So welcome again. I think we've had about 4 meetups here. A little bit of history as usual. I started this group about in October. I started doing a lot of monitoring in my day job about a year ago, and have used most of the systems out there, and gave a talk on it to the San Francisco Pro group that I was the organizer of for about 6 years here, and folks were like, "Yeah, this is cool stuff," and it doesn't look like there's a group for that here in San Francisco, so you should start one, and I did. But as it seems like it turns out there is another one too, and they're having a meetup tonight. SF Metrics meetup, I think, is across town, so it sounds like it's getting popular topic. See stuff in the news. Monotorama is next week. I think they're sold out. I don't know if I saw a couple posts on Twitter about people giving away tickets. I can't remember who it was, so there might be some available. And then what else? Velocity. Is anyone here going to Velocity in June? Yeah, it looks like there's a few interesting monitoring talks there. What else? Anyone have any monitoring related news? So thanks to Craigslist, and they are hiring. Talk to this guy, and also they have T-shirts if you want one.
Just let me know. I'll find it for you.
Okay. And so with that, I'll hand it off to the speaker.
Thanks. All right, welcome everyone. My name is Maxim Pezzoni, and I work as a software engineer at SignalFX. And in case you don't know, SignalFX is a real-time monitoring solution for modern infrastructures and applications. And over there, I actually specifically work on the real-time streaming data analytics component of our platform. Today, I wanted to share some of what's possible when you have a real-time monitoring system that works on streaming data, and in particular, how you can detect and counteract fast-evolving anomalies before they turn into a customer-impacting outage. And I call this lightning-fast monitoring against lightning-fast outages. So, SignalFX, we eat our own dog food. So SignalFX is the only tool that we use for monitoring and alerting. And personally, as a developer, I think that's amazing. Firstly, I'm lucky enough to get to work on the product that I use every day, but also it makes my life and my job so much easier every single day. And SignalFX has a very strong DevOps culture. All software engineers are part of the on-call rotation. We're responsible for all the stuff that we put into production, for monitoring it, operating it, and eventually fixing it whenever it breaks. So whatever we can do to try to optimize for the least amount of operational work, we're going to want to do that. And what I'm going to talk about today falls into that line. So what's sort of the problem that we're working against here? Today's systems are increasingly more complex than before. We have service-oriented distributed architectures. SignalFX Zone Stack, for example, is close to 30 services now. Today's systems handle large amounts of very real-time, very live traffic, a lot of stuff happening in all directions all the time at the same time. And so the systems tend to fail in new, unpredictable, and somewhat exotic ways. And sometimes you're not going to be able to catch one of those failures in time, or one of those anomalies, before it turns into something that will impact your customers. So among those failures lie the infamous lightning-fast outage. And what I mean by that is when you have a sudden meltdown of one or more of your components or services that develops from an anomaly that arises and evolves into an outage very, very quickly. And by that I mean it's usually within a minute or something. You go from everything's fine and then suddenly stuff doesn't work. So there's Usually this is caused because of some new or unexpected unusual load that is added onto your system. But of course, the specifics depend on what your system is, what it does, what is architecture. So some of example causes that you can have is if the behavior of the system is more or less tied to some user activity or user input, and you may have a sudden increase in traffic to your site. I don't know, maybe you're on the front page of Reddit or something, or could be some query was unexpectedly large results, or that's unexpectedly expensive to perform by one of your backend systems, or it could just be a bug. There's always some less traveled code paths in your code base, and sometimes you're going to fall into one of them and you have a bug there because it wasn't well tested or something like this. So those anomalies are really hard to catch because most monitoring systems are not sophisticated enough to even see them. They're either not granular or not fast enough to capture the data that it is going to show you the anomaly. So things like periodic checks, pool-based system, low-resolution system. As I said, you can very easily go from it's all good, everything works to oh god, we're all going to die, and your system is on fire. And you're not going to have the data to see how it evolved, what transpired, and how you went from it's fine and you have the beginning of your anomaly to you now have an outage. And that can be true even with metrics. If you're with us in the 21st century and you have metrics-based monitoring, you're actually a little bit ahead of the curve. That's getting a little better in the industry, but the further away you go from Bay Area tech companies, and the more you find upstream that are still somewhat stuck in the dark ages of monitoring. Especially if you go out of web SaaS companies and you go into finance and telecoms and stuff like this, it's still very traditional, like Nagios, God forbid, and those sort of things. So even with metrics, a 1 minute resolution or even sometimes a 10-second resolution on your data may not be enough to catch the anomaly or to see it evolve from the anomaly to the outage. And if you use Graphite or InfluxDB, how much do you really trust the right edge of your chart? How accurate is the most recent data on your dashboards and the data that your alerting mechanism is trying to evaluate? And especially if you do any kind of aggregation over a population of time series, how much do you trust that? And in my personal experience before I used and worked on signal effects, the last 1 to sometimes even 5 minutes was just a mess of partially reported data and very inaccurate when you do aggregations. So you're actually effectively blind to what's happening right now in your system. And then finally, there's the ultimate slow link when reacting to an alert to an anomaly. It's the on-call human. Even if you can detect the anomaly before it turns into a customer impacting outage, how long does it take you to respond to that page and do something about it? It's 3 a.m., you pull your phone up, you get blinded by looking at the screen, to take your laptop, curse 2FA for taking so long to sign in, look at some charts, eventually find a runbook if you're lucky, and then actually try to do something about it before the outage. And sometimes it's already too late. So how can we make this better? How can you work against those lightning fast outages? That's a bit of a coordinated effort between different parts of your system, and it doesn't start nor end with your monitoring system. So of course you need a fast and real-time monitoring system that can detect those anomalies quickly and is accurate in doing so even on very recent data. But you also need a dynamic application stack so that you can counteract those anomalies, and I'll go into detail into what I mean about this. And then finally, to sort of put that all together, you kind of need your very own if this then that system. But before we dive into those various elements of the solution, let me show you a little bit what I mean by how lightning fast monitoring and automated remediation can really help save your scan. So this is an example from an anomaly that happened yesterday afternoon. The data that you're looking at here is the heap usage on the 9-node cluster of the analytics service, which is at single affects the system that I work on, and that executes every day over 250,000 signal flow computations, which are little programs that perform real-time analysis on time series data. And it's sort of the backing of our technology of real-time analytics. So you can see one of them started having an issue. The heap started to rise somewhat suddenly past our CMS trigger threshold. And if you can see the times from here, everything looked fine, and then in about 10 seconds it was above the CMS threshold. Another 10 seconds it was really, really high, and probably another 10 to 30 seconds after that the machine would have died. So on the bottom half, this is the detector view, and you can see the little triangle there is when we detected that anomaly and did something about it. And you can see that very soon after, that trend reverses, and we've, in this case, successfully shedded some load out of that machine and saved that instance. So this is what I mean by being able to react to those things very quickly, and no human was involved in that process. So how does that put together? So as I said, first you need a fast real-time measuring system, which will give you observability into your system. I think the metrics are the best vehicle for getting complete end-to-end and high-resolution visibility into what your system is doing. As always with metrics, using dimensions and tags allows you to get more interesting aggregations and filtering. I don't think I'm teaching anything to anyone here. It's pretty standard. But it's also important that the data that you measure and that you collect is reported to your monitoring system in real time. So you really have to streamline that metrics reporting pipeline. And finally, on the push versus pull debate, it's kind of a hot topic in monitoring. If you ask a lot of people, they say, well, actually, it's kind of pointless and it doesn't really matter. Both are fine. I say it depends, but in general terms, a push model will usually fare better at scale than a pull model. Regardless of what Prometheus folks will tell you. When you start having tens of thousands of hosts, which is what we see on some of our customers, you can't pull that from a single Prometheus instance. You're going to have to shard this, and it gets very complicated. And especially if you're trying to get high resolution, down to the second metrics. Secondly, instrument all the things. If you want to get complete visibility into the various aspects of your system and your infrastructure, you need to develop that culture of code instrumentation. Everything new that you implement needs to be correctly instrumented and have proper dashboards and alerts set up for it. You need to instrument at all levels of your stack. The host, the containers, the applications, even in your lambdas if you use serverless architectures. But don't stop at infrastructure and somewhat, I would say, framework level metrics. Custom application metrics are often the most valuable, and they'll really show you what your system is doing, what you've implemented in action. So, application instrumentation, you really need to look at everything. Count, requests and actions and errors that you're seeing. Count how many data points you're processing or whatever you're doing, right? So, and put some dimensions on the stuff that you're reporting. So these are just some examples from our code base here and there. Our code base in Java, we use code metrics everywhere. In our case, host, service types, and instance name are added automatically to the dimensions of every metric that we report. So in our code base, we just have to really put the dimensions that are specific to what we're measuring here. Also measure your queues, thread pool size, and buffers, and number of in-flight tasks, all the sort of gauge type metrics, and also all the timers, time important code paths, wait times, response times, latency, all that stuff. As much as you can measure, the better. Next is, once you have all this data, all your metrics, you need powerful alerting on top of that. And it also needs to be fast. It also needs to be real time. It needs to work at scale on potentially large number of time series, so that you can aggregate across populations of time series and still be able to get accurate information about what's happening right now on those populations, even on the most recent data. So that system needs to be able to handle differences in reporting lag dynamically and gracefully, right? So you need to be, if one of your servers has a slight delay in reporting, you have to be able to correctly wait for that, but not too much, right? So there's some interesting algorithms here that are important for the accuracy of your alerts, and it's always going to be a trade-off between the timeliness of the calculation you're doing and its accuracy. And so finally, you also need to be able to build smart dynamic alerts. You guys all know static thresholds is often a smell in your alert definitions. You need to be able to have alerts that can compare what's happening right now with some norm, some history, and make a decision based on that instead of some static threshold. Finally, and that's slightly more of a side point, but sadly detecting causality between redundant alerts is still a very hard problem. There's, I think, a couple of companies are trying to solve that problem, but it's really difficult. And it's, in my opinion, one of the points that today is contributing to alert fatigue, where you can have the same anomaly resulting in multiple different kind of alerts from different systems when they actually correlate with each other. So for the purpose of what we're trying to do here, you need to be able to really identify the one that you're going to be looking at to take remediation action against. So again, once you have that, all of your monitoring data, and you can build good alerts on it, you need to be able to react to that and apply some change on your application. So you need to have a dynamic stack, really, all the way from provisioning to application configuration. That starts usually with an elastic infrastructure, where you can have automated provisioning, where containers make that much easier and much faster if you have to spin up additional capacity. Dynamic service discovery becomes really important if you're scaling up and down dynamically, right? So in our case, we use Zookeeper and Curator, but ECD is also there. And of course, the services that you're going to be scaling up and down need to be horizontally scalable and handle that up and down scale gracefully. It's important to consider your third-party components as well when you do this. Being able to automatically spin up new instances of some third-party service that's not your own software, and have that be part of the service discovery that your application uses makes a lot of things easier. For example, at SignalFX, like, we have a couple of third-party components like Cassandra and Search and Kafka and stuff like this, and we have wrappers around it that automatically exposes them in the same service discovery way that Curator uses. So from the point of view of our application, it's exactly the same to see, what are the hosts of that service versus what are the hosts of Elasticsearch, and we can build the client dynamically from that. So really, all that you need for spinning up a new instance of any service in our stack is what are the Zookeeper servers that you want to connect to, and everything will be in there, all of the location of all the services and all the configuration. And being able to deeply integrate that service discovery in your application framework and really embrace that in the way that you write your the different services in your stack will make that easier. So at SignalFX, as I said, we're Java shop. We use Juice pretty extensively for dependency injection. We use Thrift for RPC. We use Zookeeper and Curator for service discovery, and all of that is brought together to make talking to other services really easy. And that's just sort of like a little example here. We can just directly inject into a class an implementation of that service interface that will make Thrift RPC calls to the correct service instance that implement that service. And then doing something, you can just call a method in that interface, and that's always correctly backed by the currently advertised instances, potentially partitioned or load balanced on those backend instances, right? So all of that complexity can be very easily abstracted away from building your app, but you maintain that flexibility in your infrastructure to be able to scale up and down and move stuff around, move your containers around, and maintain the dynamic nature of the stack that's going to be very important for your remediation actions. Something else that you need to make your stack easily dynamic and controllable is potentially having some internal control endpoints. So stuff that allows you to make your services perform some operational tasks by just hitting some endpoint. That could be some internal HTTP API, JMX operations, some custom control console if you want. But you want to be able to do things like shed some load or kick off some tasks, or take your stuff out of a load balancer, or stop consuming from a Kafka topic, and you can also try to, if you have like a service that does leader election, you can potentially want to impeach the current leader and move that somewhere else if you plan on taking that host down, and have all of the, sort of these operational things a little more built into your application to make it easier to impact change on it. And finally, you need to be able to configure your app and your services dynamically. You want to be able to do real-time configuration changes that take effect immediately and control things like the size of your thread pools, the size of your queues, of buffers, to control maybe like task execution intervals, enable, disable features and safety valves dynamically. And finally, when you do so, you also want to make sure that you respect semantics for graceful degradation. Like if you turn off a feature via a feature flag, make sure that you return the appropriate error to either the other service in your stack that talks to it, or to your user if that's like you've turned off a feature of an API or something like this. So as I said, SignalFX, we use Zookeeper pretty extensively, and application configuration sits in there as well. All of our configuration properties at the environment level and the service level are in a subtree in the Zookeeper cluster, and all of the services watch that tree for changes so they can see and reflect those changes in real time in that instance. We can set up callbacks on those properties when they change to actually do something in the application. And when you pair that with real-time monitoring that I was talking about earlier, the effect of those configuration changes is directly visible in your shards in the next second. So that's just like a little example again. In our code base at SignalFX, just to see what's possible to do. We simply define our configuration as Java interfaces, and we can say, okay, this is we have the pool.threads property, and in this case, we declare it as a property of integers so that we can attach callbacks to it. We can set a default value in code. Those config values can also just be primitives, because that's easier to deal with in your code paths. And sometimes if you don't need to attach callbacks to it, could also be a JSON value that's going to be decoded for you automatically. In this case, we have just a set of strings to represent the blacklist. And then using that becomes really easy. If you follow through a little bit here, we'll have this class. It has its own config. We're going to have a thread pool executor. We define a callback that is going to be called when the thread pool size property is going to change to impact the core pool size, maximum pool size. And you can see in the actual code of the class is as easy as adding that callback. And then when we do something, we can check, okay, is that feature enabled, yes or no, and we can either submit to that thread pool or return some failed feature right away. And we shut down, we should clean that up. So that's just a sort of trimmed down example to see you like how you can build features in your application framework, in your code, to make those dynamic configuration changes impact the things you're using in your code, queues and thread pools and stuff like this, to really make your stack dynamic and control your features and give you all the levers that you need to take the remediation action to prevent those outages. So when you put it together and really, as I said earlier, build sort of your own if this then that system, you're really going from you've automated something and you're making it now automatic as a response to an alert. And really here the hardest part is how do you go from sort of tribal knowledge in the engineering's mind of, okay, how do I remediate this problem? How do I what action do I need to take when this happens to prevent the outage? And so converting that tribal knowledge into some script, some procedure that you can call is really the hardest part here. There's no silver bullet. It depends entirely on what you're doing and what your system is and what levers you have and how you want to respond to certain anomalies and things like this. In the example that I mentioned earlier, really all that is doing is looking for the highest using highest resource using computation that's on that node and just like migrates it somewhere else. And it, because of the way load balancing works, is going to fall back onto a lesser loaded instance that will be able to accommodate it. But again, as I said, what action do you take, to what extent, on what alert? That really all depends on what you're going to do. In most cases, you're probably still going to want to page the on-call person because depending on the remediation action you're taking, you may be leaving your system into a non-standard state. Like if you take an action to stop consuming from CapFQ or throttle down something to make sure that you're not going to burn your system down, you probably want a human operator to come back later and address the situation and stabilize the system and restore your configuration to its nominal levels. It's very important to test that automation, be able to exercise and validate your automated remediation actions into some kind of integration environment. Make sure you trigger them and verify that they take the correct action against your system, because it's not something that you can check at compile time that is going to work. So you have to validate that in an integration environment. And then finally, you have to put the wiring together in all this, as we said, define and verify your alerts. Things like being able to do detector pre-flighting help you figure out, okay, this is when my alert would have fired, and be able to really fine-tune your alert and see, make sure that it's going to execute your action only when it's really necessary. Use webhooks here out of your alert as a notification to trigger some Lambda function or some system that you have in your infrastructure to trigger that remediation action. You can also act on alert resolution, right? If your alert fire, you take one action to sort of save the system. When the alert clears because the anomaly is passed, you can take another action to maybe restore some settings automatically. Again, that really depends on how far you want to go into automatically restoring your system to its nominal state. Pretty important to record an audit log as the automated action takes place. Record what has been done at what time, what impact you've done on your system. You can either record that as events in your monitoring system, or if you have a PagerDuty incident, you can add that in there to show what has been done to deal with that alert. And then finally, profit, or sleep tight, because you're no longer waking up at 3 a.m. to solve your alert. So yeah, to come back to this, as I said earlier, here you have an anomal situation that develops really, really quickly within a few seconds, few tens of seconds, and we can take an action automatically. Like no one's involved in getting that system back in check, and you can see that curve, the trend inverts right back after the action is taken. So that's it. If you have any questions, I'm happy to answer them about how to put this together or about real-time monitoring systems, anything. Yeah.
So my biggest fear and the biggest objection I get to doing dynamic pool sizing and things like that is, let's say the monitoring system has an issue, or not that the monitoring system has an issue, that trend happens simultaneously on all nodes of the cluster. So
yeah.
What kind of steps do you take to safeguard against those situations?
Okay, so your question is there's always some concern about having automated processes that take action because either they may not know everything that's going on, or they may go too far, or things like this. So again, it's up to how you define your alert, right? You can set up this alert to only fire when, you know, this node is an outlier compared to the population, right? And then you know you can take localized action on that node. But for example, you can have another alert that looks at the population of nodes, and if they're all going up at the same time, then the action you take could be different, right? In this case, it could be, or I'm going to start refusing all new jobs and functions, right? Like, don't take any new load, and then, you know, shed some of the most consuming load, and hope that resolve your problem, right? So it's really up to how flexible your alerting allows you to be, and define, and how fancy you want to be in your alert conditions, right? Like you can specifically configure your alert to only fire when, as I said, when you have that outlier and not the rest of the population also going up, right? These sort of things. And for the sort of other half of your question about, you know, I agree sometimes it's worrisome to have automated processes that sort of fix stuff for you in the background and you don't really know like how far they're going to go. Like again, like there's, you know, you encode, as I said, that tribal knowledge into those actions and you know how far they can go into impacting your system. And that's why I said it's still always a good idea to maybe page someone if you know that you're making a change in your system configuration that is putting you into a non-nominal state, right? If you're no longer consuming something from a Kafka queue, or you've turned off a feature flag or a safety valve, you know, maybe you don't want to turn it back on automatically, and you want someone to take a look at it. But at least you've gone from, you've changed the problem from I have an anomaly that would evolve very quickly into a complete outage to I've detected the anomaly, put something in place to get graceful degradation, right? Maybe now I'm returning 503s instead of no answer at all, right? Or you know, or try later, right? And then you have time for the human on call to go in and look at what's going on and restore the system. But at least you don't have, you know, your component is not on fire, potentially cascading down to others, right? Because it's, for example, in the case of a rise in heap like this, the problem is what happens if you run out of heap is you have a full pose garbage collection, right? Which is much more damaging to the other systems that query that analytic service, because now they get timeouts and stuff like this, right? If instead they can get a fast, immediate response that's, you know, hey, try later, right? Or it's rejected right now, you know, you can turn around and say something useful to your user, as opposed to something that just hangs and holds up a thread on that other service that also is not going to have issues. So it's really about containing the anomaly to something manageable, but where you need to be fast to do so before it turns into a customer impacting outage.
Do you do something there, like say open a circuit breaker if that situation like that arises?
Yeah. So again, it depends on the levers that you've built into your application, right? Like feature flags and throttling and all that stuff, right, are all things that you can control dynamically when you have some kind of like dynamic configuration system like I described, that allow you to trick those circuit breakers and say, okay, I'm going to stop accepting new load, I'm going to, you know, reject requests and stuff like that. But at least it can be done gracefully, right? You can return meaningful error codes in that situation. Any other questions? Or, yeah.
You mentioned before static thresholds, kind of smell,
Yeah.
which I totally agree with. How do you detect an anomaly like that, for instance?
So in this case, I'm sorry if this is going to sound a little bit like a sales pitch, but in signal effects we have what we call sort of like detector functions, like packaged anomaly detection, where all I really had to say is this abnormal compared to the historical norm? And then I have some parameters that I can tweak about how long is the historical window and how much of an outlier I want it to be for it to trigger. And it pre-flighted that alert for me, and it would show me across the history, like this is where it would have fired. And when I set this up, and it fine-tuned and found the cases that are similar to this. right? And you configure it so that it finds it, quickly enough, right? But not so quickly that it would fire all the time, right? Because you can have variations, so it depends on what you're looking at. But here the alert worked perfectly, and in this case it's computing a historical norm over some historical window and looking at how many standard deviations away from that norm the current value is. And I think in this case it's set to, if it's 1.5 standard deviations above that historical mean one. So it's a historical moving average that is a certain window sometime in the past. So it's like 15 minutes that ends 5 minutes ago, something like this. And then if the current value is 1.5 standard deviation above that moving average, then it's an alert. Okay. So defining those alerts are actually pretty easy when you have a monitoring system and an alerting system that uses computation and analytics on the time series data, and that can do it in real time. Because you have all the power of mathematics that you can imagine, percentiles, moving average, standard deviations, and all that toolkit that you can put into your computation and your alert definition to really get the signals, the correct signals, and then just do that comparison. That's it. But as I said, of course, I don't want this to turn into a Excel speech, but you can imagine having this in other systems. I suppose it just, what I really like about our product is it makes it really easy to do this. It's either a couple of lines of our signal for language or a couple of clicks in the UI.
So in regards to resolution time, how how long would something like that take to resolve? It looks like maybe around 30 seconds or 15 seconds.
Yeah, I mean, so in this case, it took about 20 seconds for the alert to fire after it started being a little weird, and then it's going to come down. How fast it comes down depends on the system. Here, once we've shedded that log, garbage collection still has to do some work to get rid of it, right, and clean up the heap. So it's going to come down however fast it wants to. But the trick is to find that sweet spot between detecting it fast enough and being accurate in detecting it without false positives and stuff like this. And so that's why being able to, as I said, pre-flight view alerts is super useful for that, because you can really see over any kind of historical period, this is how it would have behaved, and then okay, if this happens again in that same magnitude, I'll catch it, and I'll catch it within those 5, 10, 15 seconds.
So and then you define an action to take based on the intent.
Yeah. So then this alert fires a webhook, triggers some function, some procedure that then turns around and says, okay, in the payload of the webhook, you have the dimension of the source of the alert. You know what host it is, what service it is, what instance, and from that we can look it up, and again in service discovery, we know where it is, we know what port to talk to, or what configuration setting to change in Zookeeper in that environment, and that's it.
Can you get into a little bit more detail about your automation for testing these actions? Because you mentioned there's a CI.
Yeah, I mean, so as I said just now, you trigger those usually by a webhook. So it's very easy to craft.
So I'm curious. Are you piping historical data into that CI, or is that actually an isolated part of production where you're just continuously doing these things over?
Yeah, I mean, you execute that suite of tests however often you want. But the key is to you manually trigger the remediation action, and you verify that it impacts the system in the way you expect. Right? So if the remediation action is to turn off a feature flag, right? You're gonna send that payload to that to trigger the remediation action, and then your test goes in Zookeeper and verifies that configuration property has been set to the expected value, right?
Okay.
Right. Or
I'm curious mostly because if you have, so I mean, just in my mind, if you're continuously doing this, the system changes, right? As I push more code, like the system sort of behaves a little bit differently every single time. Like, for example, you're using the shedding example.
Yeah.
Maybe I add a code and start shedding a little bit more slowly, then now the test breaks. I'm just worried
yeah,
that
I mean
it's
that's
very brittle.
that's always the, I mean that's always the case. Like if you change your code and the behavior of the system, your tests sometimes have to adapt.
Okay, so but
yeah,
I guess,
there's no mystery.
is there any tricks around that, or like
No,
it sounds very brittle to me? Like every single
Again, I mean, again, it depends on your remediation action, right? I mean, it's a lot of the stuff that a lot of the actions that we take here are changing the value of a configuration flag in our configuration system in Zookeeper.
Okay.
So that's very easy to test, and that doesn't really change.
Okay.
Right? Then, like confirming that this has the impact that you want in your code, like that's another part of your test, right? That's unit testing on your code.
Yep.
Making sure that when that config value, right, in the you see the code where
Yeah.
I use the config, right? That when that config value is set to this, you take that correct action, right? But you test that with unit testing. In our case, you have this config interface. You mock that. You set whatever return value you want. You exercise your function. You verify the correct behavior, right? It's completely separate testing than the testing of this automation.
Right. Okay.
Yeah.
Do you have any good stories about, you know, in the early stages, like if something went horribly wrong, that you learned something from?
From the automation?
Yeah.
No, I mean, you have to be really, really careful when you deploy it.
Okay.
So you test it, you verify it, you set, you know, you kind of have to get a feel for how much leeway you want to give your robot, right? It's,
Okay.
yeah. So it's we don't do it at a very broad scale yet, right? It's but this one is an example, right? So, and yeah, the question just.
You mentioned the right edge problem, so I'm
Yeah.
wondering what kind of, how do you solve that with the signal effect stuff?
So the way that we approach this problem is that we, as the computation ingests data in real time, right? So you have a set of time series that your computation is looking at. So in this case, 18. We dynamically measure the lag of those time series as they come in, right? So a point will have a logical timestamp, and then when you receive it, that's your lag. So that lag is measured at the ingest point of the platform, right? But it's persisted and rolled up with all the data points. And when we receive this streaming data, or when we query historical data, and it all comes into the analytic system, we know what the lag of those points were. Right? So it means that we can establish, before the computation starts, we can establish a delay baseline, right? Like based on the historical lag behavior of this time series, we know how much we can expect them to be late, and we keep dynamically updating that baseline as new streaming points come in and have their own lag information, and that basically tells us how long we're willing to wait for data to come in for each logical slice of data, right? And you can set constraints on that, on how long you actually want to wait. And it doesn't mean that you're going to wait this long, right? If all data shows up, you're good, right? You can move on. But it tells us how long we should wait if we have to.
I don't see how that's, you still have to do something, you're still essentially just waiting for the edge to show up.
Yes.
And it's just not displaying
But
the edge if
yes.
we don't expect it to be there.
Yes.
Versus.
But the difference is you can control, as I said, that trade-off. Right. Now you get to control the trade-off between accuracy and timeliness. Right. So, depending on the reporting behavior of your data, for example, like CloudWatch data, for example, is 1 minute resolution, but it's only available every 5 minutes, right? So every 5 minutes you can get the last 5 minutes of data. So you can have a point that's like 4 minutes late, a point that's 3 minutes late, 2 minutes late, 1 minute late, and a point from now, right? So that lag keeps doing that seesaw. But you can imagine the same for truly like streaming data, where you can have variation in this delay, and it can impact some of your hosts, right? Maybe suddenly one of the AZs that this system is spread across has a slow network, and there's an extra second in reporting. You probably want to be waiting for that second. But again, you can set a maximum of how long you truly are willing to wait. And usually the trade-off falls towards timeliness when you're looking at a graph, and it will fall toward accuracy when you're trying to have an alert on it. But again, the important part is that at least you can control that trade-off. Any other questions? Cool. Thank you for your time.
Thank you.